Yes, sir. The control is yours.
Yeah. Okay then.
You can share the screen also.
Yes. Okay. Yeah. So let's start the new subject, which is communication theory. It's a huge one, correct? Communication theory. 1 second again. I have to take all the control color, white color. Okay. Yes. Okay. So communication systems or communication theory I call because we study only theory. Okay, right. So in this a huge subject. In this we will have multiple sub subjects. One is analog communication. Okay, first topic which we study is analog communications, in which we talk about amplitude and angle modulation. That is the first topic. So next we will talk about uh, probability, random variables, and random processes. Okay. So this is especially for ECE students. So if you don't know this, don't call yourself a communication engineer. Okay. If you don't know probability, random variables, and random process, so it is shame on us to call ourselves a communication engineer. Okay. So next, let us talk about digital communications. Okay, digital communications. Okay, first we'll talk about analog communication, then we talk about digital communication, then we talk about information theory, and finally we will talk about error control coding. Okay, so these are the topics we have for communications. Okay, so I think analog communication is there even for instrumentation. Digital part of digital communication is there for them, but all these topics are there for ECE students. Okay, so the textbooks I usually follow are communication system engineering, communication system engineering. This is the title of the textbook by Prayakis and Salehi. Prayakis and Salehi. This is a nice book, and also a lot of textbooks are there, but most of the material will be covered from this textbook. Okay. Yes. So this is a good textbook to buy. Okay. So don't use any local author books here. It's not that they are bad, but most of the textbooks are not that good. Okay, so they all copy from foreign textbooks, so that's why we prefer foreign, especially for circuit branches. We follow only the foreign author textbooks. Okay, right. Mostly don't follow the local author textbooks, any subject in our field. Okay, so many textbooks are there. Modern the digital communications is also covered in this textbook, but I have a lot of textbooks, so I'll compress everything and give it to you. Okay, so but you, if you want any textbook to follow, you can follow this textbook. Okay, yes. So till now, any doubts here? So for this, there is special book, probability, random variables, and random process. Same title. Who is that? Athanasios Papoulis. Okay, and Unni Krishnan Pillai. Same title. I think probability, random variables, and stochastic process is the title. Fourth edition is available in the market. Okay, so when we were studying, fourth edition came, and after that no revision. Okay, and same title, one more book is there, Woods, Stark and Woods. This first edition only is there. Okay, they did not revise it, and it's a very good book. Stark and Woods is really a good book. Okay, so digital communication, a separate textbook is there, just by Proyakis. Okay, so just by Proyakis. Fourth edition is available in the market, but yeah, so I don't think this is necessary for you as far as gate is concerned. Okay, so this book is enough. And for probability, random variables and random process, this book is enough. Okay, and information theory anyway is there in this textbook, even error control coding. Okay, yes, yeah, but yeah, multiple textbooks are there for each topic, but especially for last 4 topics there are a lot of textbooks, but we prefer this one. Okay, right. But from gate, for gate also they are giving from this textbook, just like that they are copying and giving the questions. At least 4 5 problems they have given from this. It's not that all problems are copied, but yeah, most of them, like at least 4 5 times they gave directly questions from this textbook. It's a big book, a lot of problems are there. It's a nice book. Okay, yeah, till now any doubts? Okay, so let's directly jump into the first topic, which is analog communication. So this is olden days way of communication. Okay, first we should study, so we cannot forget the past, right? So analog,
Sir,
yes,
in this, mostly the syllabus for instrumentation is also covered. Right.
yes. Oh,
Most
parallelly
of
both
them are instrumentation combined, right?
first and third அவ்வளவுதான் for instrumentation.
Okay, okay, okay.
இது இன்னும் ரெண்டு இல்ல,
Mm.
but I prefer you attend this also.
Okay, sir.
Last two தேவையில்லை.
Yeah,
But
fine, sir.
because see, digital communication, if you want to understand, you should understand this one.
Okay, okay, okay.
That's why. Okay, so if you have time, please attend. There is no compulsion, because you should
Mm.
have studied probability random variables anyway in mathematics.
Okay,
But
sir.
random process, you should not, you could not study. I think you did not study that, correct? But
Yes,
our
sir.
treatment will be
Random
different.
variable. Right.
Yeah, yeah, you should have studied, but our treatment will be completely different. That you will see.
Yeah,
Okay.
okay, fine, sir.
So here we don't toss balls, green balls, red balls, and all that. அதெல்லாம் இருக்காதுங்க. Okay. Pure theory. We will have pure theory here. Okay.
Okay, sir. Oh, sir, one more doubt, sir.
Yeah.
Uh, how much time will it take to, sir? Can you hear me?
Mm. Yeah, yeah, I'm hearing you, but
Yeah.
not hearing you.
Like how much time, like tentatively you can say, right? Communication theory.
Tentatively up to Pongal, I'm planning. Saturday, Sunday, we
Yeah,
will have
fine.
4 4 hours.
Yeah, that's fine, sir. But I'm
Yeah.
just wondering. Yeah.
Pongal week.
One.
And the Pongal week வச்சிங்க.
Yeah,
So
fine.
what
All right,
is
sir.
the date here? Fourth, and the Pongal week is, so when is Pongal? 14th, huh?
Yes, sir.
Yeah, so
14,
14,
15.
15, 16, 17, let us say.
Yeah, okay.
Okay, so till 17th, I think we'll get almost like 30 hours.
Yeah, fine. Okay,
So
sir.
that is enough, I think, at least.
Yeah, that's okay, sir. Okay,
Yeah.
sir. Thank you, sir.
Yes, yes. After that, I think it's enough, correct? You require some time for preparation also.
Yeah,
So
okay, sir.
yeah,
Yeah, yeah, that's okay. Yeah.
correct. So tentatively up to 17th, okay, va? Maybe it may spill for 2 days, but that's
Yeah,
okay.
yeah, that's okay. Yeah,
Yeah.
okay, sir.
28th வரைக்கும் வச்சிங்கப்பா, ஓகேவா?
Okay, sir.
Maximum 28th. அதுக்கு மேல I won't take the class.
Yeah,
Okay.
fine, sir.
Yes. Okay. So still any doubts here? Okay. No doubts. So from, I think from tomorrow onwards, we will plan at 6:15 itself, not at 6:30, so that 2 to 3 more hours can get added. We will see. We'll discuss. But tentatively 6:30 to 8:30. Okay.
Yeah, okay, sir.
Yeah. Any doubts here? Okay. So let's move to the main topic, which is analog communications. Okay. So in this, there are actually, in a normal communication system, there are two types of communication. So one is called baseband communication. Okay. So baseband communication, in which what we do, signal is directly sent through the channel. Okay. So signal is sent directly through the channel. Okay. So whatever I am speaking, it directly goes to the channel. For example, in olden days, we had that telephone wires, right? So that is a dedicated channel. So whatever we speak will go through that telephone lines. That is called baseband communication. But if you want to send the signal to a very a person who is very far away from us, baseband communication will not help us, right? So in baseband communication, examples are what you call telephone lines, and also coaxial cables, etc. Dedicated lines. Okay, so dedicated lines, if you have, you can send the signal through the channel. But what is the main disadvantage of this? What is the main disadvantage of baseband communication? You wanted, for example, you want to talk with a friend who is in Delhi, let us say. So what happens if you use this baseband communication? You should require a connection from Chennai to Delhi. So it incurs huge money, right? So you should, if you want to lay some telephone line or if you want to lay a coaxial cable, definitely it will the amount of cost involved is very large. Okay, and what is the second disadvantage? Second disadvantage is because baseband communication means whatever I'm speaking. So it is high frequency signal or low frequency signal. Yes, speech signal or video signal. So these are the only two signals for us, correct?
High frequency, sir.
Yes.
Low frequency.
High frequency or low frequency?
Low,
See how much frequency my throat can generate here? Maximum.
low, not more than 20,000.
That is audible. Speaking. I cannot generate 20 kilohertz from my mouth. I can generate only maximum 3 to 4 to maximum 5 kilohertz. All of that. Audible range is 20 to 20 kilohertz. That's different. Allah.
Yes, sir.
So I can listen from 20 to 20 kilohertz. That is okay. But I cannot speak more than 5 kilohertz. Is it okay? So highest frequency possible for a speech signal is how much? 5 kilohertz. So means what? It is a low pass signal. Is that okay?
Yes, sir.
5 kilohertz is reasonably low pass. Similarly, video signals, audio signals. Why do I say that? Why? Because present sample and next sample, will there be drastic change or very little change?
Little change.
Little change. Why? For example, if you say that is a waveform. Okay. So definitely what happens if you take this sample and next sample, the amplitude difference is very small. Is it okay? Means what? The signal is varying slowly. Even though it is 5 kilohertz signal, if you look at the waveform, then you can see that the present sample and next sample or previous sample, their amplitude values are very close to each other. Means what? The signal varies slowly and hence our speech signal is a low pass signal. So similarly, video signal or image, all these signals are what? They are low pass signals. Is that okay? Is that okay?
Sir, I have a doubt,
No.
sir.
Hmm.
சார் இப்போ நம்ம பேசும்போது நாய்ஸும் இருக்குல்ல, பேக்ரவுண்ட் நாய்ஸ்.
நாய்ஸ் இப்ப கன்சிடர் பண்ணல. அந்த ரெண்டாவது டாபிக்ல தான் கன்சிடரேஷன்.
ஓகே ஓகே. அது
இங்க இருக்கல இது.
ஓகே சார்.
நான்
ஸோ அதோட ஃப்ரீக்வன்சி ஹையா லோவா? அதுவும் லோ தானே?
அது ஹை. நாய்ஸ் will have high frequency. We will do filtering at the receiver end. அது வேற. அது அப்புறம்.
ஓகே ஃபைன் சார்.
ஓகே, இப்போ வந்து we assume that what? There is no noise.
Yeah, okay.
Okay, so noise is good or bad because you raised that. See, I always ask this to students. Noise is good or bad here? Yes.
Depends.
Usually.
Bad answer.
Why here?
நம்ம பேசுறது கரெக்டா ஒழுங்கா கேட்கணும்.
Okay, அந்த பக்கம் கேட்கணும்னா you should அந்த you should have a noise free signal, correct?
Yes, sir.
Let's assume there is no noise. Will we have jobs? அந்த perspectiveல பாருங்க. Yeah, I want noise free signal. That is a requirement. But let's assume that there is no noise. Whatever I speak directly come to you without any disturbance. That is what I wanted. But let's assume that there is no noise. What will happen?
No need to.
No need of communication systems at all, correct?
No need of
Probability,
higher technology, yeah.
probability, random variable, random process தேவே இல்லை நமக்கு.
Yes, sir.
Correct. Digital communications தேவே இல்லை. Nothing is required. So whatever you speak, that will reach you. So what is the need of communication system? ஒரு modulator, demodulator இருந்தா போதும். Correct?
Yes.
Yes or no? But what happens if there is noise? If there is noise, what will happen? That fellow will throw a challenge for us, correct? So once a challenge comes into the picture, definitely jobs also comes into the picture, correct?
Yes.
Yeah, so we will have jobs only if there is noise. So that's why you should be grateful to signal or noise.
Noise.
Noise will give you food, not the signal. Okay. So because there is noise, what will happen? That will, I'll explain. So for example, in digital communication, what will happen? We will send ones and zeros. Yeah, we will talk about this also. Don't worry. But at the transmitter, what you will send here for one, let us say you send a positive rectangle. You don't usually send rectangles, but let's assume that. For zero, you send a negative rectangle. So the waveform which is sent through the channel will look like this, correct? For one positive rectangle, so this is our x-axis. For zero, negative rectangle. For one positive, positive on the mari. Is it okay?
Yes, sir.
But this is sent through the channel, correct? So what will channel do? If this fellow is nice to us, he will add noise, correct? To that. So how does the signal look? Let's say noise is very small. So how does the signal look here? It looks like this, correct? Huh? Correct.
Yes, sir.
This is the waveform which is received at the receiver end.
Okay.
Now, what you will be expecting? Transmitter will say that Macha, I sent one. Okay. But what you will receive? You will tell him that Macha one varlada in the mari waveform vandichi, correct?
Yes, sir.
But what transmitter will say? I sent one which is a positive rectangle. So it is up to you to decide whether one is transmitted or zero is transmitted. Correct? Huh?
Yes, sir.
So this fellow, he receives this waveform. It is this fellow's headache, receiver's headache to tell whether it is one or zero. So then what he will do? He will make a decision. Correct? What decision he will make? If many ways to make a decision. Let us assume this is x-axis. So what he will do? Let's say this is the bit duration and the bit total duration. Okay. So in this bit, he will take area of this waveform. Correct? Huh?
Yes, sir.
And he'll say that if area is greater than 0, then what could have been transmitted? 1. If the area, for example, next bit, what happens? Area will become negative, correct?
Yes.
So if area is less than 0, what could have been transmitted?
0.
0. So with that logic, reconstructed signal would be what?
1.
Reconstructed signal at the receiver. So what do you get? You get 1. Because here area is negative, you get -1 or 0, correct? And after that, here you take this is positive. You take this, I'll write down that so that you will understand. Oops. Okay, so this is positive area, this is negative area. Here you get positive, positive, negative, negative, and positive. Let us assume that. So because of that, what happens? You get a complete reconstructed waveform which is like this. Is it okay?
Yes, sir.
That is what it means. What you have reconstructed 1 0 1 1 0 0 1. Okay, wa? Is it not beautiful here?
Yes,
You
sir.
send the signal through the channel. Channel does its work. What is that fellow's work? To add
Noise.
noise. He added the noise. Channel has added the noise. But with your what you call intelligence, what is that you have? Some intelligence you have used means what, taking the area of each waveform in a given time period, and based on that decision, you reconstructed the signal. So is there any error here between transmitted and receiver signal?
No, sir.
No error. That is the beauty of digital communication. Is that okay? Why you should have digital communication and not analog communication? In analog communication, what you do? You send the signal directly through the channel, correct? What will channel do? That fellow will add noise. Okay, what will we receive? We receive a noisy signal, correct?
Yes.
Whatever you do on this, still there will be noise. Whatever processing you do on the received signal, still there will be noise. Okay, so that we cannot overcome. So that is the main disadvantage of whom? Analog communications. Okay, so if there is noise, if noise is getting added to your analog signal, let us call this as message signal m of t. So what will happen? This flow is nothing but m of what will we receive? The message signal plus noise. Message signal plus noise. And what we do, we know that there is noise in the signal and hence we pass it through some low pass filter, but that low pass filter cannot remove complete noise. So what will be the output of low pass filter? Still it will be noisy message signal. Is it okay? But if you go for digital communication, what we do, this message signal is passed through what is called, I directly write that PCM, okay, pulse code modulator. This fellow will give what as output? Ones and zeros. Okay. Yes, this ones and zeros. See here in digital communications, what is happening? Transmitter is much cheaper. Okay, so transmitter is much cheaper and receiver is costly. Why? You have to reconstruct the signal at the receiver end. Okay, so one output of this pulse code modulator would be ones and zeros, and these ones and zeros, if they are passed through channel, the received signal will be noisy ones and zeros. By using some logic, you try to reconstruct the signal, and if your logic is good enough, then reconstructed signal and the transmitted signal are exactly same. So indirectly it means what? You are exactly reconstructing the transmitted signal. Is that okay? Is that okay? Yes.
Yes,
So
sir.
here you should be thankful to whom again? Noise. He's adding only less noise, correct? What happens if noise is very large? That is also possible, right? When there is heavy rain, what you will do here in your TV, you'll get some nice, beautiful message. What is that?
Due to, sorry for inconvenience.
Sorry for inconvenience. So why? Because reconstruction is not possible. Because what happens because of heavy raindrops? What will happen? The electromagnetic wave will get distracted, and the reconstruction at the receiver end will not happen properly. What happens? Let me draw that waveform also. If the noise is very large, I'll rub this one so that I can draw here. Okay. So if noise is very large, the waveform can look like this. Correct? Same thing. Okay, large noise. This is the waveform of the received signal. Correct. If the noise is very small, so this is low noise. Large noise during heavy rain or maybe clouds, thunderstorms and all that, you get this kind of waveform. So what will the receiver, if you use the same logic, correct? So let's say this is our x-axis. So if you use the same logic, so take area. So first duration, what you get here? Area to be negative, correct? Next you get area to be positive, then positive, negative, and so on. So what will be the reconstructed output? That will be 0, 1, 0, and the madhya varum, correct?
Yes, sir.
Yes, means what? We have made an error, correct? Even though who is transmitted? 1 is transmitted. You are telling that 0 could have been transmitted, correct? And the next bit is what? You have actually transmitted 0, but you reconstructed it as 1. So definitely you are making an error. So then what happens? Our error control coding algorithm will come and check whether you are properly doing it or not. If there is error, what happens? It will wait for a few seconds and then it says, sorry, you are doing mistake. So let us stop the reconstruction process. And that's why you get that inconvenience message. Is that okay?
So can we use electromagnetic signals for weather predictions then?
For obviously radar, so weather radar, what they do,
Yeah, yes.
correct?
Yes.
IMD will tell you, right? Heavy rains, how do they do? They do only by using radars.
Yes.
Okay, weather radars are there, so they will penetrate. See, if there is no clouds and all that, electromagnetic wave directly will enter, right?
Yes, sir.
To her. So there they will check how much is that multiple parameters are there. So in normal scenario, what are the parameters? During the cloudy season, what are, I mean, if there is heavy storm and all that, so what is the parameters? So then they'll compare and check and tell what happens. Okay.
Yes.
Yes, electromagnetic waves are everywhere. So if you want to see through wall, correct, who is the person other side, at that time also they will use radars. Okay, they are called through the wall radars, and human monitoring, if you want, that also can be done using radars. They are all non-invasive and they won't wear. For example, if you want to measure my heart rate and respiratory rate, how do you measure here? I keep a radar there. So radar will send the signal, and because of my heartbeat and respiratory rate, okay, if I take respiration, I don't take 72 times per minute, right? So respiratory rate is different, heart rate is different. What is heart rate normally? It will be from 70 to 80. Maybe it can go up to 100, correct, for a normal human. Respiratory rate would be less. You don't exhale and inhale 72 times, correct? So maybe 10 to 15 times. Okay, so that rate and also heart rate, all those things we can estimate using radar. So all these things are coming in automotive driving. By I'm telling all this is because I am working on that. So they are called vital signs. Means what? You are going in a automotive, what you call automotive radar. So completely automated. So there is no driver. You are sitting at the back side of the car, and car itself is running. So every time we will try to monitor the heart rate of the patient, heart rate of the passenger, okay, who is sitting in the back. Okay, I'll be reading some paper or doing some my work, but there will be a radar sitting in the back side of the driver's seat, and that fellow will be always sending the signal, uh, signals, and based on that signals every minute I will try to estimate the heart rate and the respiratory rate. Okay, if there is change continuously, so then what will happen? My car is directly connected to cloud. Okay, so car will send a signal to nearby hospital that so this fellow is having abnormal heart rate and respiratory rate, please attend him. Okay, and automatically the car will stop next to road, and he will give his location to the hospital, so ambulance will come and pick you up. So all these things are possible. Okay, but yes, radars are there everywhere. Okay, is it okay?
Yes, sir.
Yeah, so like that, they are called vital sign recognitions. Okay, there are multiple ways. So only heart rate and respiratory rate we are estimating. Multiple things you can estimate. Okay, so for example, drowsiness. Let's say it is automated, not automated driving, but assisted driving. So you wanted to check whether driver is drowsy or not. Okay, and all those things you can check, and everything should be non-invasive. Okay, so something penetrates into the body and nobody will allow, correct? So from outside only you have to extract all the information. Okay, so technology is improving a lot. Okay, let's come back. What were we talking? Yes, if there is large noise, so then definitely what will happen? The reconstruction process may go wrong, and because of that we may incur errors in each bit, and how much error we have incurred, that is estimated using what is called probability of error estimation. Okay, we'll talk about that later. Okay, any doubts here till now? Note that we did not do any modulation. We got ones and zeros, we sent through the channel. So that process again we call it as what? Baseband communication. So when signal comes, you just pass it through the channel. That we call it as baseband communication. Is that okay? Whether it is analog communication or digital communication, doesn't matter. So in analog communication, what happens? You have analog signal, directly pass it through the channel, then it is called baseband communication, analog baseband communication. Okay, yes, now you have analog signal, you have sampled it, you quantized it, and finally you got pulse code modulated output. That means you got all ones and zeros. Take those ones and zeros and pass it through the channel, then that is again called what? Digital baseband communication. Still we did not do modulation. Okay, so if you don't do modulation, whether it is analog or digital, we call it as what? Baseband communication. Is that okay?
Yes, sir.
Sir,
Yes,
baseband communication only signal directly channel send பண்றது
correct.
நாய்ஸ் அதெல்லாம்
Noise இருக்கும், noise இருக்கும்.
அதுக்கு ஒண்ணுமே இல்ல.
அது see, நம்ம what is our duty? Our duty is to design a transmitter and
ரிசீவர்
அவ்வளவுதான். In between channel is not in our hand, இல்லையா? அது அவன் கையில தான் இருக்கு. We cannot do anything.
ஓகே சார்.
Okay, that's why he throws a challenge for us. Correct. Channel நம்ம கையில இருந்தா we can do whatever we want, அல்ல?
Yeah, okay.
But channel is not in our hand. So that fellow, so channel, it's a free space for us actually. So free space, and how many sources are there? Infinite sources. That biggest star, which is called, what is that yet? I forgot its name. Betelgeuse, something. It is 1 million times larger than sun, it seems. So if that also will cause some headache for us. Okay, so I just wanted to add some fun. Yes, definitely he will add to noise, but very little, because he's very far away from us, so it is very little. Okay, yes. Okay, so yes, so the indirectly I told the advantage of digital communication here, right? So usually you should be thankful to channel. Why? Channel usually will introduce low noise. In normal scenario, there won't be much noise. Okay, very less noise only he will add. So he's very good to us, and hence again we should be thankful to noise. If noise is very large, then what will happen? The algorithm which you develop for suppressing of the noise also will become much complex. So heavy mathematics will come into the picture. So, but because noise is very gentle with us, he will add only very small noise to our original signal. So, and he will allow us to get it removed nicely. Okay, right. You will understand how small it is. Noise n of t, how small it is, you will understand. Okay, right. Usually that will be very small. If it is large enough, then we are screwed again. Okay, so in analog communication, even that small noise again will cause a problem. Okay, right. Okay, so if you don't do any
சார் சேனல் வந்து வயர்லெஸ் சேனல் மட்டும்தான் இருக்கு.
if any channel we can take, wireless இல்ல, coaxial cable, telephone lines என்ன வேணா எடுக்கலாம்.
சார் அப்ப நாய்ஸ் வந்துட்டு அதுவா சேனல் ஆட் ஆகுது தானே சார், நாம எதுவும் ஆட் பண்றது இல்லை.
அதே ஆட் ஆகும், கரெக்ட். நம்ம ஆட் பண்றது இல்ல.
ஓகே சார்.
சேனல் will add noise. ஓகே
சார் பட் நாய்ஸ் வந்து நம்ம எந்த ப்ரொபோர்ஷன்ல இருக்குன்னு கண்டுபிடிக்கிறது வந்து பண்ணலாமா சார்?
thermal noise you have studied, right? In our EDC la, thermal noise, collision of two electrons, they are random alla.
Yes, sir.
Yeah, there whatever noise is generated, that is called thermal noise. So that noise will be added if you send it through coaxial cable or telephone lines. Okay,
Yes, sir.
but free space lo pona different types of noise. So for example, somebody kicks his scooter, because of that spark, what happened, that is electromagnetic wave alla. So once spark comes in your scooter, what happens, you will have that spark plug alla. So that fellow will be always ignited, so that fellow will be sending electromagnetic wave, you don't see that. So that also can affect our signal. So அந்த மாதிரி நிறைய scooters இருக்கு, நிறைய cars இருக்கு. So all those things will add to the noise. Is it okay?
Yes.
Yes boss. Okay va?
Yes, sir.
Okay.
So, like for high frequency speech, sir, should the rate of speaking should be more or the loudness? Like,
Loudness comes with amplitude alla.
yes, like, but even with loudness, can the rate change, sir?
Which rate?
Frequency, higher frequency.
No, that won't change. Amplitude, if you see, they are independent alla.
Yes, sir.
Amplitude and frequency of a signal are independent, so they are not related with each other. Okay,
So, but in case of human speech, sir, like with louder speech, like noise, then we'll be having different variation, right? Then
correct. See, if you have a louder voice, then definitely what will happen, the noise usually will be very small, then it is easy to segregate between the signal and noise. Correct.
yes, sir.
So in that way you get better output. If
Yes,
the amplitude is very less and it is comparable with noise, then it is tough to segregate both of them.
yes, sir.
Okay,
Yes, sir.
yes, still any doubts here? Okay, yes. So I write. So there are two types of communication. So first type is baseband communication. Okay. So and second type we call it as what? Passband communication. Second type of communication is called passband, and first type of communication is called baseband. So here what do? We directly send the signal through the channel. In passband communication we don't do that. So here what we do a process what is called modulation. Okay, so process called modulation. But I raised a question before. What is that? If you want to talk with your friend in Delhi, so definitely baseband communication is ruled out. Correct? Because the coaxial cable or telephone lines, they are very costly. To use them it is very tough, and hence we have to take the other route. What is that route here? The air route. Correct. So which is, I mean, the free space. So we should take the help of free space. Why? Because electromagnetic wave travels with what velocity? Electromagnetic wave travels with
Speed of light, sir.
speed of light. Okay, where speed of electromagnetic wave is almost not exactly equal to speed of light, but less than speed of light. Okay, so electromagnetic wave will travel with velocity of light. So obviously the signal will reach much faster. But for this to happen, what should we do? Okay, for this to happen, what should we do? We should take the help of antenna. Correct? Correct. So you are in Chennai. So you have an antenna here. Your friend is in Delhi. He also has an antenna. Here we have some satellite. Okay, so something like this. Okay, so what you do, you send the signal to the satellite and that fellow will send to your friend. But if you want to transmit the signal, sorry, the reverse potential. Okay, so if you want to transmit the signal through the free space, okay, so if the frequency of the signal is f, minimum antenna height should be equal to lambda by 4. Okay, so to transmit a signal of frequency f, okay, frequency f, we need an antenna of height lambda by 4. So what is lambda here? We know that electromagnetic wave travels with velocity of light. So what should be lambda?
Wavelength of
Wavelength. In terms of frequency, lambda equal to C by F. Is that okay?
yes, sir.
Planck's equation, correct? Max Planck.
Yes, sir.
Yes, Max Planck is the guy who first identified Albert Einstein, or else Einstein would have gone. Planck found out that Albert Einstein is a great guy. He personally went to Einstein. He invited him to take a professorship in the university and so on. Then rest is history. Or else Einstein would have been in the same patent office in Switzerland as a clerk. Okay, right. So just like GHRD helped Ramanujan, Max Planck helped Einstein. Okay, right. So this is Planck's equation. So lambda equal to C by F. Okay, so just for understanding. So for example, I want to send my speech signal. Okay, so let's take F to be equal to how much? Our speech signal. Let me take 3 kilohertz. Is that okay? If F equal to 3 kilohertz, lambda would be equal to how much? C is how much here? 3 into 10 power 8. Correct?
Yes, sir.
Meters per second by 3 kilohertz and 3 into 10 cube C by F. So that should be equal to 10 power 5 units
Meters.
meters. Okay, so that equal to how much are 100 kilometers. Correct? Is it correct? 10 power 5 meters and 100 kilometers. So this implies lambda by 4 equal to how much? 25 kilometers. So your antenna height should be 25 kilometers. Is it possible? Impossible event. Correct. Burj Khalifa itself is 1 kilometer. After that, it's very tough there. Okay, so a lot of air will be there. So building an antenna of 25 kilometers height is ruled out. Okay, right. So definitely it is not possible. So if you want to send my speech signal directly through the free space using an antenna, what will happen? It's an impossible event. So what should I do? So we want lambda by 4 to go down, correct? So lambda by 4 should go down, or no? Who should go down here? Lambda should go down. If lambda should go down, C is what? It's fixed.
Yes, sir.
Einstein proved that velocity of light you cannot change. So that is fixed. So if you want to reduce lambda, what should increase? F should increase. Okay. F should increase. If F increases, what will happen? Lambda decreases. When lambda decreases, lambda by 4 decreases. When lambda by 4 decreases, what happens? Antenna height also decreases. Is it okay? So radio Mirchi, what is the frequency here?
98.3.
90 வச்சுக்கலாம் ஓகேவா 98.3 megahertz. Is it okay?
Yes, sir.
Correct. It is a frequency modulation, 98.3 FM. Ala. So it's a frequency modulation, but still what happens to lambda? Lambda C is not going to change. So 3 into 10 power 8 divided by 9 into 10 power 7. Correct? 90 megahertz.
Yes, sir.
Okay. So what will happen here? This fellow is gone. So 30 by 9. So 3 times 3. So that should be 10 by 3. Correct?
Yes, sir. 3 point.
Meters. So lambda by 4 would still be less, 2.5 by 3 meters. Okay, so that should be the minimum height of the antenna. More than that, it's okay for us, but minimum height should be how much? Lambda by 4. So this is practical, or a metal electricity. If you rotate antenna, that will become an antenna. Correct. So that is called helical antenna. So radiation pattern will be in one direction. So you can send the signal to the, in your colleges you should have studied, you should have had your local FM. So this is what happens. That will be very small circuit. So why? Because antenna height is very small. Okay. Any antenna, you take a copper wire and rotate it, just like put your finger and that rotate and send the signal, and it will send. Why? Because radiation pattern is focused in that direction. Okay, that's okay. Let us not understand that. Okay, so if you want to send the signal through free space, antenna height should be small, and to have a small antenna height, you want the frequency to be large. But your frequency is how much? I cannot change my frequency. I cannot go more than 3 kilohertz, correct? So that is my fixed frequency. So, but I want to travel through free space. So definitely what should I do? I should take the help of another guy called carrier. Okay, so that fellow will have high frequency. Okay, so what will I do? I will sit on the carrier. My frequency is 3 kilohertz, but carrier frequency would be like 90 megahertz. This 90 megahertz in your radio Mirchi is what? That is carrier frequency. Okay, 98.3 megahertz. Mahatmachi they will tell, right? 98.3 or 90.3. 98.3 la radio Mirchi. Okay, yeah, let's say 98.3. So that is what? That is a carrier frequency. Is it okay?
Yes.
So what I do, whatever that fellow is speaking, right? Radio jockey, whatever he speaks, what happens here? That signal is actually message signal. So that cannot be more than 3 to 4 kilohertz, but that signal will be modulating the carrier frequency, and that signal is sent through the channel. Okay, and reverse process happens at the receiver. So during this process, what happens? This we call it as channel. Ala. So here also noise will get added up. Here also noise will get added up. Is it okay? That we'll talk about the noise part later. Is it okay? Any doubts here? So what is the summary? If you want to send the signal through free space, the antenna height should be as small as possible. And for this to happen, what should we do? We should take the help of a carrier. So it is some other signal. Okay, we should take the help of the carrier, and we can transmit and to transmit that carrier signal, we require small antenna height. It is similar to, so just understand that you want to go from your house to, let us say, nearby, let's say I'm talking from, let's say, T Nagar bus stand to, let's say, Adayar. How many ways you can go here? 2 ways, correct? There are 2 ways to go. So what is that? You can walk. So that is called baseband communication. So definitely it will take a lot of time to reach the destination. So if you want to reach the destination much faster, what you will do here? There is multiple ways to reach again from T Nagar to Adayar. So one is you take what? From T Nagar bus stand, you take some bus and go there. Okay, so that is one. Or you can pick up you can take the help of bike or auto, whatever. But every time you're taking the help of a carrier, correct? You alone are not going, you're taking the help of the carrier. So let's assume that you are going by the public transport. Let us say you have MTC bus you have taken. Okay, so how many ways you can travel, you can reach the destination using MTC bus here? One is you can sit on the bus and travel, and you can sit inside the bus and travel, correct?
Yes, sir.
Correct. So sitting on the bus is like amplitude modulation. Bus is the carrier, correct? So you can sit on the bus and travel, that is like amplitude modulation. You can sit inside the bus and travel, that is called angle modulation. So which is best? Sitting on the bus is best, or sitting inside the bus is best?
Inside.
Inside the bus. So frequency modulation is better than amplitude modulation. But if you want to sit inside, what is that you have to do? You have to pay money, correct, for ticket. If you sit on the bus, no need. Correct. Bus day celebrations you should have seen, right? The people who are inside the bus, they will pay money. Who are on the bus, all the students who are making lot of noise, they won't pay ticket. But suddenly the driver brakes. What will happen? The fellows who are outside only, they will fall. Who are inside, they will feel the jerk, but they don't fall. Is it okay? So definitely, who is better? FME angle modulation is better, or angle amplitude modulation is better?
Angle.
Angle modulation. But for angle modulation you have to pay more money, in the sense the channel bandwidth is large. For angle modulation, channel bandwidth, if you want to transmit a signal of bandwidth b hertz, if you use frequency modulation or angle modulation, what happens? The channel bandwidth would be very large. Your signal bandwidth is, let us say, 3 kilohertz, but you require around 150 to 160 kilohertz of channel bandwidth. But channel is in whose hand?
Government.
Government of India's hand, correct? Channel is in government's hand, so definitely you have to pay money for them. If you want more bandwidth, you have to pay more money for the government. Is that okay? Is that
So,
okay? Yes.
so there is this thing called ham radios, right?
Mm.
So, like, is it free? That is free, right? In the sense, why don't they require money for
No,
that?
that is other part of discussion, not part of gate. Okay. Yeah. Is it okay?
So,
No, we are talking about channel bandwidth, all of that. So money wise, we are not worried at all. Correct. See, in our complete communication system, we don't talk about economics and finance. Okay.
yes, sir.
Yes. Okay. Any doubts here?
சார்
Hmm.
இப்போ ஃப்ரீக்வன்சி நம்ம கேரியர் ஃப்ரீக்வன்சி வச்சு நம்மளோட மெசேஜ் சிக்னல் வச்சா அது மாடுலேஷன், அதான் பாஸ் பேண்ட்.
Correct.
அப்படி இல்லாமல் பண்ணீங்கன்னா 25 கிலோமீட்டர்ஸ் ஆஃப் ஆண்டனா ஹைட் வேணும்.
Correct.
அது வந்து பேஸ் பேண்ட் மாதிரி.
Correct. Baseband கிடையாது. We cannot send.
Yeah, exactly.
So you have to take the help of passband.
Okay,
There is no
okay.
other go.
So
Correct.
the channel cannot be free space in baseband, right?
Channel cannot be free space in baseband. Correct. Provided your frequency is very large. Transmitted signal or 100 megahertz வச்சிங்க.
Okay.
Then you can have, but it is not possible. See, in regular communication systems, what are the signals here? Speech, video, image, அவ்வளவுதானே?
Yes, sir.
But all these are what signals? They are low frequency signals, means they occupy only small frequencies. Kilohertzல தான் இருக்கும். அதோட maximum 4 megahertz will be for video. Still it is very small, அல்ல?
Yes,
When you compare it to 3 into 10 power 8, let us say f is 4 mega or 3 megahertz. What will happen? Correct. For
Yes,
example, video, இது வந்து 3 megahertz வச்சிங்க. What will happen here? This will be 3 into 10 power 6. This flow will become 300 meters, huh? 100 meters.
Yes, sir.
100 meters. Anna, lambda by 4 would be how much?
50
This
meters.
should be 50 meters. Still it is big only, right?
Yes, sir.
Yeah, so still it is not possible. Signal through cell phone, Korea. Is that okay? Or video அனுப்புறீங்க. So how do you send? Correct. If you want to send a signal or video through from your cell phone, you cannot have 50 meters antenna height in your cell phone. So definitely what should we do? This flow should increase drastically. Correct?
Yes, sir.
Yes. So இது increase ஆயிடுச்சுன்னா இது குறையும். Lambda
Okay.
by 4 will reduce. So for example, இது பாருங்க 2.5 by 3 meters, it's almost like 1 meter. Practically possible. Correct? But still in your cell phone, you cannot have this frequency. Correct? The 90 megahertz chance illa. So still more, it will be like 150 or 160 megahertz, your operating frequency of cell phone. That's why your antenna can be embedded in your cell phone. Okay.
Yes, sir.
Yes. Okay. Any doubts here? Yes. So what is the fundamental disadvantage of baseband communication? If you want to use free space, the antenna height is impractical, and hence you have to take the help of carrier. And if you take the help of carrier, that type of communication, we call it as what? Passband communication. Is that okay? Wireless communication was first invented by whom? transmission between two distant points using wireless communication. Who is the first fellow to do that?
Graham.
No. Hmm? Who is that great man?
Tesla.
Tesla. Okay. He gave credit to Marconi, but actually this fellow has done first. Okay, Marconi got Nobel Prize,
Yes, sir.
but actually this fellow before Marconi itself he has done, but Marconi stole this fellow's work. Tesla was like was in very bad shape when he fought with Edison. Correct? Edison said that DC motors are better than AC motors. Correct? Anyway, DC motors, if you want to use, what will happen at every building should have a DC motor. Correct, because it is not the alternating current and what will happen, the waveform will move like this. Correct, alternating current, we have 50 hertz like this. Correct. So let's say this is the transmitter. So what happens, you have I will just explain. I have a coaxial cable like this, right? Transmission lines. Let's say from Neyveli Lignite Corporation, we have a transmission line like this. Okay, so what will happen here, at the transmitter end, what you do, you give a sinusoidal wave of very high amplitude of 60 hertz and amplitude to be very large, right? So how much they will generate, they'll talk in terms of kilovolts, correct? Or megavolts, I don't know. These guys, electrical guys, will talk about that. So there will be transformers and many things, so that all the transmission will happen in a nice way. But here what happens, you excite the transmission line with a sinusoidal waveform, correct? Correct. Our frequency is how much? 50 hertz. You know that, right? Our operating frequency in India is 50 hertz. Is
Yes,
that
sir.
okay? Yes. So India and Europe, it is 50 hertz, and in Japan and US, it is 60 hertz. That
60
doesn't
hertz.
matter. But if you have this kind of waveform with 50 hertz, what happens there? For positive waveform, what happens? It is positive voltage, Leah. So let us talk about that. So I have a positive voltage. And how does the electron moves for positive waveform? இங்க ஒரு எலக்ட்ரான் இருக்கு, let's assume இது மெட்டல் அல்ல, அலுமினியம் மெட்டல், or let's say it's aluminum metal. So for positive half cycle, what happens here? Is positive. If you have positive voltage, what will happen? Electron will move in this direction, correct?
Yes, sir.
Yes, for positive half cycle. For negative half cycle, what happens? Electron will move like this, correct?
Yes,
Yes,
sir.
sir.
Yeah, so this flow will oscillate here itself. For positive half cycle, he will move towards positive plate. For negative half cycle, he will move away from the positive plate. So this electron also oscillates similar to that of the sinusoidal wave, correct?
Yes, sir.
Yes, because of oscillation of electrons, what will happen? Heat, okay, adu okay, but leave heat. Because of oscillation, electron move ஆயிடுச்சுன்னா என்ன வரும்?
Like signal, light.
Electricity.
Current வரும், correct?
Yes, sir.
Yes,
Correct.
sir.
So current in this circuit varies with respect to sinusoidal variation, correct?
Yes, sir.
Because electron moves like a sinusoidal way, that flow will generate what type of electricity?
I know.
Time varying electricity, correct?
Yes,
Time
sir.
varying electricity வந்துச்சுன்னா automatically என்ன வரணும்?
Yes.
Time varying electricity is
Frequency.
there means
Yes.
magnetic force also should come into the picture, correct? Yeah, time varying electricity produces time varying magnetic field, correct?
Yes,
Yes,
sir.
sir.
Correct. Yes. So, and how are they related with each other? They are perpendicular to each other, correct?
Yes,
Electric
sir.
field and magnetic field are perpendicular to each other. Is it okay?
Yes, sir.
Yes,
Yeah.
sir.
So now if you take this one, what is this rule here? Right hand rule,
Yes, sir.
correct? So let us say this is electric field. Okay. So this is the cable on which current flows. Electron moves like this. Okay. Can you see my hands?
Yes,
Yes,
sir.
sir.
Yeah, so let's say here we ignite, this is a coaxial cable, transmission line which goes. So here you apply sinusoidal waveform. What happens here? Electron will move like this, correct? Because of this, like this, positive cycle, it moves like this. For negative cycle, it moves like this. Is it okay? That electron is on this metal, aluminum cable. Because it is a metal, definitely they will be in conduction band, correct? All the electrons will be in conduction band and they are free to move. Once you apply positive voltage, what happens? Electron will move in that direction. For negative half cycle, he will move in the direction. So means what? Our electron will oscillate sinusoidally, correct?
Yes, sir.
Electron on coaxial cable will oscillate sinusoidally. Because of that, what happens? Electric field will generate like this. Electric field also would be sinusoidal. Is that okay? Because of sinusoidal variation of electric field, sinusoidal variation of magnetic field will happen. Correct? And this is E. This is H. This is which direction here? This is E and this is H. What is this direction? Huh.
Direction of propagation.
Propagation direction. That's correct. This E, this H. So this one the E cross H. Correct?
Yes, sir.
Cross product. This I have two vectors A and B. A cross B எப்படி இருக்கும்?
N cap, yes, sir.
Perpendicular to both of them. இந்த ரெண்டும் already perpendicular இருக்கு. So perpendicular to both of them is again direction of what?
Propagation.
Propagation. So but that is an electromagnetic wave, correct? But electromagnetic wave in free space travels with what speed?
Light speed.
Velocity of light. So அங்க on பண்ண உடனே immediately you will get the power. Why? It is not the electrons which will travel and come to your home. Who will come to your home?
Electric.
The electromagnetic wave across the coaxial cable will come and exit electron in your home. Okay. And from that we can generate the DC and all these circuits will run because of that. Is it okay?
Yes, sir.
Okay. So where is electric field electricity produced? It is produced at far away location. So that is the beauty of alternating current. Why? If you use alternating current, what happens? Tesla has seen that electromagnetic wave will be formed in the direction of the coaxial or in the direction of the transmission lines. Okay, and he understood that E cross H, which is the pointing vector, which you should have studied in electromagnetics, that would be the direction of the propagation, and that fellow travels with velocity of light, and hence what happens? Once anga switch on panna odane, immediately you will get the power at your home. But he is very far away, right? Those machines are very big and they are very scary. So just assume that those kind of big machines below your apartments or homes, how scary it would be, right? Tesla said that DC machines are not good for urban people. You cannot have those kind of DC machines at your location. So the machine should be very far away, and from if anything happens there, nothing will happen to the people inside the cities. Correct? So that is the beauty of alternating current. Okay. So but yeah, he fought very badly with Edison. Edison was like, he was making a lot of mockery of Tesla. Yeah, Edison is one way is good guy, but after he became a businessman, he became very bad. Okay, he was a very bad guy. So history sees him as a bad guy. Initially, he was a good man, but later, yeah, because he was also poor man when he was doing all the experimentation. He was a poor man, but after that, after he saw money, he became very greedy and he discarded all other people. So Tesla also, he was admiring Edison. He was when he was in Czechoslovakia. As Tesla is from Czechoslovakia, so he was admiring Edison. But when he came to Edison, he was explaining to Edison that AC is better than DC. So Edison, as a okay, you prove that I am correct. I mean, prove that alternating current is good. Then I will give you $50,000. And full daily 20 hours he worked for 10 to 15 days, and finally he came up with a draft showing that AC is better than DC. And he showed to Edison. He said, "That's good. You have done a good job. Go to work." That's all he said. And Tesla asked him, "You said you'll give $50,000. It was fun, yeah." Don't take it seriously, he said. So Tesla got very much irritated and immediately he quit. But he didn't have job. Correct? He came from Czechoslovakia. 10 days or 15 days he was with Edison. That's all. He was on daily wage, daily some $8 to $10. That's all per day. So within 20 days he quit the job from Edison, and he was having no money at all. So he was doing coolie work. He was building construction sites. He was to take all the what you call the sand, all those bricks and all that he used to put in on his head, and he used to do all that work. He is not, but his mind was working very hard. Okay, so it's not that he gave up. Okay, so he is a socialite in the sense he didn't marry. So Tesla did not marry, so he thought that that is a obstruction for his work, so he didn't marry. But he was a good socialite, so he had a lot of friends and all that. One fine day, the fortune struck him. Okay, so then remaining part is history. But because he did not marry and he did not have family, at the last stages he lost all his money, and finally the Westington house who supported Tesla, so they were giving him rent and some peanuts. Okay, so they were giving him, and finally one fine day he expired, so nobody cared him, and in his lodge, he was in a lodge, so he expired. Nobody noticed. After 3 days only, when smell was coming out, they noticed that there is some dead body inside, and by that time it was completely like a dilapidated state, his body. Okay, so he had a bad end. Beginning, yeah, initially also he was having a bad beginning, so he almost died in the beginning. Okay, he got some typhoid. He got typhoid, and his father said that if you survive, I will send you to engineering, or else you have to become a priest. So luckily he survived, then he became engineer, and all this happiness, whatever we are seeing, because of him. Okay, so that's the reason Elon Musk named his company not Edison but Tesla. Okay, right. So look at great people. So you look at the lives of them, and definitely should get inspired. So you are enjoying this happiness, whatever you are having, correct, is because of Tesla. So all the happiness is, most of the happiness comes from what? Apart from food, from our gadgets only, right? Whatever gadgets you have at your home. So just imagine without AC in Chennai in summer, how it will be. Okay, all those things work because of Tesla. Okay, Tesla and another great guy by the name Michael Faraday, right? You who should know him. So these two fellows combination is deadly combination. Both of them were very poor, and they had very bad life. Okay, so luckily Faraday had family, and hence he had a good end, but not for Tesla. So Tesla, he was bitter rival of Edison, so that really screwed his life. Edison, wherever he went, he denigrated Tesla. That is very bad. He may be jealous of Tesla, but you should not pull him down, because he's a great man. Tesla is really brilliant. Okay, so Marconi is one of the guy who stole Tesla's work. When they fought, finally Tesla said poda dai vechi koda அந்த மாதிரி he told Marconi. அதுக்கு தான் he got Nobel Prize. So just think Tesla getting Nobel Prize, that would be, his life would have been different. So all the royalty he gave because of AC current, that could have made him the billionaire at that time, around at least $4 billion. Think in 1930s 20s, $4 billion, so that is almost like 400 billion now. So that much rich he could have become, but he gave up. And he almost invented transmitting of electricity through free space, through antenna. So now we don't do, but he had some idea, it seems. One fine day, all his work were burnt. We don't know who burnt it. He himself burnt, or it happened naturally, we don't know. So, and because of that, he became what you call, very much depressed, and he stopped talking to people. After that incident, he stopped talking to people, and he was talking with the pigeons. Okay, he was talking with pigeons. He engaged his last days of his life with pigeons. Okay, so in that way it went. But yeah, that's bad. Now everybody says that Tesla is great and all that. What is the use yet? No use. When he was alive, you should respect him. After that, after death, who knows what will happen? Correct. So now we say Tesla is great, man. He's that, he's this, but you should recognize him before. Same happened with Alan Turing. That also bad ending. Same happened with Armstrong, who invented FM, Mirchi FM. Because of him only, he also had a bad time with IBM and all that. Companies, they screwed his life. Okay, so sorry for that. Yeah, so let's come back to our main topic. Okay, yes. So just now we understood that baseband communication is not possible through free space. Okay, and hence we have to go for what is called passband communications. How do we do this passband communication? So passband communication is done. Okay, passband communication is done with the help of carrier. We want somebody's help, and that fellow we call it as carrier, done with carrier signal. Okay, given by, let us call that as C of t, which is equal to A of t multiplied with cos of I can say omega ct plus theta of t. Okay, so this we call it as general carrier signal. Okay, usually sinusoidal signal would be like a cos omega ct plus theta, correct? But we have written in this form like a of t multiplied with cos omega c. Okay, right. So we call this as general carrier signal. If a of t is linearly varied. Okay, so linearly varied with the message signal, with the message signal m of t, it is called amplitude modulation. Okay, so it is called amplitude modulation. Why amplitude of the carrier? Correct, amplitude of the carrier is varied with the message signal. How are we varying here? We are varying linearly with the message signal, and hence we call this as amplitude modulation. Okay, you always think like a bus. You are sitting on the bus. What is the bus here? Cos omega ct plus theta of t. Adar mela you are sitting. Correct. That's why we call it as amplitude modulation. Okay. Is that okay? We'll talk about message signal soon, but whatever I'm speaking, we can call it as a message signal that usually represented as m of t. Okay. Now, if omega c, which is the frequency, is linearly varied with message signal m of t. This implies we are talking about what? What is omega c? What is omega c?
Carrier frequency.
Carrier frequency. Okay, carrier signals frequency. So carrier signal frequency, if it is linearly varied with message signal, we call it as frequency modulation. Okay, frequency modulation. Okay, and finally, if theta of t, what is theta of t here?
Angle.
Angle. If angle of the carrier, right? If theta of t is, or we call it as a phase. Okay, so if theta of t is linearly varied with m of t, we get what is called phase modulation. Theta of t is called phase, and if you vary that theta of t linearly with message signal, we call it as phase modulation. Okay, and these two combinedly we call it as angle modulation. Angle modulation means it can be frequency modulation or phase modulation. Is that okay?
Yes.
Yes. Okay, so first let us talk about amplitude modulation and then let us go to angle modulation. Okay, so first let us talk about amplitude modulation. Okay, so before we go into the details, first we should know what is a message signal. Okay, so usually message signal we call it as m of t. Okay, it can have any shape, and let's assume that that fellow's Fourier transform is this one. Okay, okay, minus 2 pi b to plus 2 pi b. Okay, so this is our message signal m of t, and this is our corresponding Fourier transform m of j omega. Okay, so what is the assumption? Our message signal m of t is band limited signal. Okay, with bandwidth of how much here? What is the bandwidth?
4 pi b. No, 2 pi b. 2 pi b.
In hertz.
Uh, b.
1 by
B hertz.
B.
Okay. B hertz. Okay, hopefully you know that, right, from our Fourier transform chapter. Okay,
Yes.
yes, this is our message signal, and that message signals Fourier transform is m of j omega, whose shape can be anything. So I took this funny shape, and this flow exists from minus 2 pi b to plus 2 pi b. And what is the bandwidth of the signal? That is highest positive frequency. Positive frequency alone contribute to the bandwidth, and hence bandwidth is how much? B hertz. Is it okay?
Yes, sir.
Okay, so usually Fourier transform need not look like this, but our message signal m of t is what? It is real. Correct?
Yes, sir.
M of t is real, and the Fourier transform would be what?
Real.
Fourier transform. What here? Suddenly signal real and Fourier transform. What will happen?
Magic.
Conjugate.
Conjugate symmetric. Correct? If m of t is real, Fourier transform would be conjugate symmetric. And if you take in terms of polar form, what will happen? M of j modulus of m of j omega is equal to modulus of m of minus j omega. Means what?
They are
Magnitude of the Fourier transform is what?
Even.
Even. That's why we took this plot. Okay.
symmetrical.
Yes. Fourier transform is even. I mean, magnitude of the Fourier transform is even. Other angle irukum, but we will usually discard the angle. Is that okay?
Yes, sir.
Yes. Okay. So hopefully you understood why I took this one. Okay. So what is the first question that may come? Sir, Fourier transform symmetrica eppadi irukka mudiyum? Correct. That is not required. But because our message signal m of t is real, its Fourier transform is conjugate symmetric. And from that we have proved that the magnitude of the Fourier transform is even. And that motivated us to take the spectrum shape in this form. Okay.
Yes, sir.
Okay, angle will be there, but usually we don't consider that. For the magnitude mattum, it's enough for us. Is that okay? Yes. Any doubts here? Any doubts? Okay. So if there are no doubts with this brief introduction about the message signal, we will talk about the first topic, which is called double sideband suppressed carrier modulation. Okay, double sideband suppressed carrier modulation. Okay, so in this what we do is we have a message signal m of t. Okay, so that fellow is multiplied with the carrier signal cos omega ct, and the product is sent through the channel. Okay, so that product is sent through the channel. That's very simple circuit, right? You have a multiplier, you give m of t and cos omega ct to that multiplier. So whatever output you get, that is sent through the channel. So let us try to write down what is equation at A. Okay, so what would be equation at A? That would be m of t, and that we call it as phi dsb sc of t is equal to m of t multiplied with cos omega ct. Okay, so output is phi dsb sc of t. Okay, so phi dsb sc of t is m of t cos omega ct. So what will happen to corresponding Fourier transform? This implies phi dsb sc of j omega would be equal to how much here? Which property we have to use? You remember? M of t cos omega ct. So what is the Fourier transform?
The convolution.
Which property?
Shifting.
Shifting in frequency domain. Yeah, convolution in frequency domain, you can do that, but we have already talked about modulation property, you remember? So this fellow will have 1/2 times m of
Cos omega c.
j omega plus omega c plus m of j omega minus omega c as the Fourier transform. Okay. Yeah, so let us try to plot that Fourier transform. And how does the plot look? So the Fourier transform, what it will do here, you have to shift to the right by omega c and left also by omega c. Okay, so this is minus omega c and this is plus omega c. Amplitude would become half. So this point would be omega c minus 2 pi b. This point would be omega c plus 2 pi. Okay, so this is our phi dsb sc of j omega. Okay, yes. So in this, whatever is there above omega c, that is called upper sideband, just for terminology, and whatever spectrum we have for frequency less than omega c, we call it as lower sideband. Okay, and same rule on the negative frequencies also. So this is our LSB and this is our USB, upper sideband. Okay. And what happens to the bandwidth here now?
Omega.
What happens to the bandwidth? Actually, bandwidth should be positive frequency, right?
Yes, sir.
What is highest positive frequency? Omega c plus 2 pi b, and hence bandwidth would be fc plus b hertz, correct?
Yes, sir.
That is the ideal bandwidth, but practical bandwidth is equal to, so practical bandwidth would be equal to how much? This width, only in the region where this flow is positive. So that we call it as 2b hertz. Okay. So practical bandwidth would be 2b hertz. Okay. Ideal bandwidth would be how much? So ideal bandwidth is fc plus b hertz. So we will consider only practical bandwidth. Is it okay?
Yes, sir.
Yes. Okay, so this is the after multiplication of m of t with cos omega ct. What happened? The Fourier transform got shifted and bandwidth has become how much here? 2b hertz. Okay, in modulation techniques, we talk only about practical bandwidth, not the ideal bandwidth. Is it okay? In signals and systems, we talk about what bandwidth? Ideal bandwidth. But here we talk about practical bandwidth. Okay, so what is the practical bandwidth of modulated signal? What is the practical bandwidth of modulated signal? Which is 2b hertz. What is the message signals bandwidth? What is the message signals bandwidth? M of t bandwidth. How much is that? We took the M of t bandwidth is how much? B hertz. Okay. Message signals bandwidth is B hertz. Modulated signals bandwidth is how much? 2b hertz. And what is that we have to send through the channel? Modulated signal or message signal?
Message signal. Modulated signals.
Modulated signal. But what is the bandwidth of modulated signal?
2B hertz.
2b hertz. So what is that we have to do? Channel should allocate how much bandwidth here?
2B.
2b hertz. Okay, channel should allocate 2b hertz of bandwidth to transmit our message signal m of t, whose bandwidth is just b hertz. Message signal's bandwidth is b hertz, but to send modulated signal, you require how much bandwidth? 2b hertz. It's good or bad?
Bad.
Bad. Why? Our message signal bandwidth is b hertz. Instead of paying for b hertz, you have to pay for
2B hertz.
2b hertz. So in that way, that is one of the disadvantage of what? Amplitude modulation, especially double sideband suppressed carrier modulation. What is the main disadvantage? the transmission bandwidth is how much? 2B hertz, which is twice the bandwidth of the message signal. Okay, so we'll take down that as note. Okay, so what is that note here? The transmission bandwidth of 5 DSBSC of T is equal to 2 times the bandwidth of M of T. This is the disadvantage of double sideband suppressed carrier. But what is that we are doing? What is that we are doing? We are in a position to transmit our message signal M of T through the channel. That is the advantage we had. But what is disadvantage we have to face? We have to pay more for channel bandwidth. Okay, we have to pay more for channel bandwidth. That is the main disadvantage of amplitude, especially double sideband suppressed carrier modulation. Okay, so name itself suggests that it is called double sideband. Why? We have two sidebands, one is upper sideband and one is lower sideband, and hence it is called double sideband. And why it is called suppressed carrier? Why? Because if you have a carrier, what is the carrier signal here for us? What is the carrier signal? Cos omega ct. What is the Fourier transform of cos omega ct? What will be the Fourier transform of cos omega ct? What is delta of omega plus omega c plus delta of omega minus omega c and multiplied with pi, correct?
Yes.
Pi times delta of omega plus omega c plus delta of omega minus omega c. Are they visible here? There should be two Dirac delta functions at where? Plus or minus omega c, correct?
Yes, sir.
Are they visible? Are they? Can you see two impulses here?
Yes, sir.
Where here? I don't see anything, correct?
Okay,
No,
sir.
no impulses, right?
Yes, sir.
You have the spectrum. All the spectrum of M of T is there. That's all. You don't have two Dirac delta functions at plus or minus omega c, correct?
Yes, yes, sir.
Implies what? That implies carrier is suppressed. Is that okay? And that's the name. That's why it is called suppressed carrier. In Fourier transform, what is happening? In Fourier transform of M of T cos omega ct, we don't have the Dirac delta functions explicitly at plus or minus omega c, and hence this type of modulation is called suppressed carrier modulation. Is that okay?
Yes, sir.
Okay, so please write down that. As there are no, 1 second here, a lot of noise, I'll come in a minute. Yes, sorry. So hopefully I have written that as the spectrum of DSB-SC, okay, as a spectrum of DSB-SC of T or DSB-SC signal, as spectrum of DSB-SC signal does not contain Dirac delta functions at plus or minus omega c explicitly, does not contain Dirac delta functions at plus or minus omega c explicitly, comma, this type of modulation is called suppressed carrier modulation. This type of modulation is called suppressed carrier modulation. Is it okay? Any doubts here? It's very simple, right? No need to do some heavy mathematics, simple mathematics. What is that? Just multiply message signal m of t with whom? Cos omega ct. So that fellow will take care of everything. But hopefully you should appreciate now Fourier transform, correct? Directly in time domain, we cannot reveal anything. But in frequency domain, if you go, what happens? You can see the spectrum shifted to the right and left by plus or minus omega c, and we can see that transmission bandwidth is how much? 2 bHz, which is the disadvantage of this suppressed carrier modulation. Is that okay? Any doubts, please? Yeah.
Is it
Yes.
preferable? Is it not preferable that direct signal should not exist? Is there any condition of that?
No, if you just multiply m of t with cos omega ct, by looking at the spectrum, we got that information. Got that there are no impulses or no Dirac deltas at plus or minus omega c. Adakaga we have to give some name, alla. That's why we call
Yes,
it a
sir.
suppressed carrier modulation. Is it
Yes,
okay?
sir. Yeah.
Okay,
Okay.
இப்போ இருந்தா என்ன ஆகும், that we will see later.
Okay.
Okay, right. Any doubts? Okay, so let us summarize. In double sideband suppressed carrier modulation, what we do, we modulate. Modulate means what here? English meaning modulate. Anna enna? Singers will modulate, alla? You will have heard. You should have heard, right? SP Balasubramaniam or Siddhi Sriram, they will do a lot of modulation. Means what? They will change. Correct? Change. That modulation means what? Change. Amplitude modulation means what? You change the amplitude of whom? Of the carrier with whom? Message signal. That's why it is called amplitude modulation. Is that okay? You are changing the amplitude of the carrier. What is the amplitude of the carrier here? Here,
1.
1. That fellow has become what now after multiplication? Initially it was 1, now it has become m of t. So what happened? We have changed the amplitude of the carrier, which is initially constant, with m of t. That's why it is called amplitude modulation. Is it okay?
Yes.
Okay. And who is doing that change? M of t. That's why this fellow is called modulating signal. Okay. Our message signal, we call it as modulating signal. After modulation, whatever we get, we call it as modulated signal. Okay, so that is all terminology. Okay, but that's okay. We should know that. Okay, the signal which changes the amplitude of the carrier, that fellow is called modulating signal. The signal after modulation, whatever we get, that signal is called modulated signal. Is that okay?
Yes.
Yes. So this modulated signal's frequency is how much now? That modulated signals frequency is how much? That fellow is centered initially. That fellow is centered at where? Centered at omega c. Omega c is very large or very small?
Large.
Very large. Okay. So what is the requirement? We require antenna height to be as small as possible. Correct?
Yes, sir.
So what should be the carrier frequency then? It should be as large as possible. So this is the requirement for amplitude modulation. Is it okay? Omega c should be very much greater than 2 pi b, or in terms of fc we can write fc is very larger than b hertz. Okay, for amplitude modulation to happen. In the sense, if you want to send a modulated signal through the free space, we want antenna height to be as small as possible. Indirectly, it means our FC should be as large as possible. Okay, so typically this ratio is there, right? FC by B, that would be around in hundreds. Okay, typically 300 to 400. Practically, I mean, in practical circuits, they require this ratio, means this really large number, right? FC and B. Okay, so typically FC by B is very large, 300 to 400 in our practical circuits. Is it okay? To send DSB-SC signal through the channel, we want FC to be very much larger than the bandwidth of the signal. Okay, right. Is it okay? Any doubts here? Any doubts? Okay, so what is the main disadvantage? Transmission bandwidth of DSB-SC signal is how much? 2 Bhz. Okay, that is the main disadvantage of DSB-SC signal. Okay, so let's assume that we have transmitted the signal through the channel, and luckily channel did not add any noise. So that is assumption. Okay, so what happens at the receiver end? So that we call it as DSB-SC demodulation. Correct. So receiver end, you should get down, right? So if you look at the analogy of bus, you're sitting on the bus. At the destination, you have to get down. You cannot always sit on the bus. So the process of getting down, we call it as demodulation. So what is that you receive at the receiver? Yes, you receive 5 dB SC of T, correct? That signal is received, and at the receiver end, again what you do, you multiply with cos omega ct. Okay, and the resulting signal, let us call that as B. Okay, now let us analyze what is the signal at B and corresponding Fourier transform. So what is the signal at B here? What is signal at B? You get phi DSB SC of T multiplied with cos omega Ct, correct? And we already know DSB SC of T is how much? M of T cos omega Ct multiplied with cos omega Ct, which is nothing but M of T cos square omega Ct. By doing simple math, you can see that this is equal to M of T by 2 plus M of T by 2 cos 2 omega Ct. Is it okay? Any doubts, please? Okay. At the receiver end also, you should have an oscillator which will generate this frequency, this sinusoidal signal cos omega Ct. Transmitter also should have an oscillator, correct? This is cos omega Ct is actually output of an oscillator. So that oscillator should generate how much frequency? Omega c. At the receiver end also, you should have a similar oscillator which generates exactly omega c frequency. Okay, so now Fourier transform at B is equal to how much? M of T by 2 will have what is the Fourier transform here? M of j omega by 2, correct? Plus what is the Fourier transform of M of T cos 2 omega Ct? 1 by 2 is already there, so you get 1 by 4 multiplied with M of j omega plus 2 omega c plus M of j omega minus 2 omega c. Is that okay?
Yes,
Correct. It is M of T. This is looking like again what? M of T cos omega naught T means you have to shift to the left and right by omega naught. Omega naught is how much for us? 2 omega c. So let us plot the Fourier transform here. Fourier transform at B. Okay, so this is very unconventional way of teaching, but hopefully you understand that. Okay, so Fourier transform at B is how much? M of j omega by 2. Is it okay? That is our m of j omega by 2 minus 2 pi b plus 2 pi b. What happened to this fellow? M of j omega plus 2 omega c means that spectrum will shift to the left by minus 2 omega c and also to the right by 2 omega c. But what happened to the amplitude? They become 1 by 4. Where are we now here? At the receiver end or transmitter end?
Receiver.
Receiver end. So receiver wants your message signal, correct?
Yes, sir.
Is it okay? So what out of these three spectrum, whatever you are seeing, which one we want at the receiver end?
First,
Middle one, left one, or right one?
middle one.
Middle one. Why? M of t Fourier transform is this one, correct? So what is that you have to do? You have to pass our M of this Fourier transform at B through whom? Through whom? I want only that part, right? So if you want only that part, you have to pass the signal at B through whom? I want only that part. Means I should pass it through whom?
Low pass.
Low pass filter. Okay, so we have to pass it through low pass filter. Okay, with a bandwidth of B hertz. Okay, and what will be the output here? What will be the output? In Fourier domain, you get m of j omega by 2. In time domain, you get 1 by 2 m of t. Okay, so that would be the output of low pass filter. So finally, we got our m of t back. Half is a scaling factor. That's okay. So we pass this through an amplifier. You can get back your m of t. Is that okay?
Yes, sir.
Yes. So if you pass the signal at B through low pass filter, what happens? Only the spectrum centered at origin will come out. That is what we want. Remaining two, we don't want them. So they will be suppressed by the low pass filter. So automatically we get in time domain 1 by 2 m of t. Okay, and this we call it as what? Demodulation. Getting back your message signal m of t, we call it as demodulation. But what is that you are doing? You are using the same carrier frequency which is used at the transmitter, and hence we call it as what? Synchronous detection or coherent detection. Okay, as carrier frequency at transmitter and receiver are exactly same. This type of demodulation. Okay, so this type of demodulation is called names, right? Same, they are identical, exactly same, is called what? Synchronous detection. Synchronous detection or coherent detection or demodulation, whatever. Okay, coherent means what? Same frequency. That is the meaning of coherent. That's why it is called coherent detection. Okay, another synonym for coherent is synchronous. Both are same. Omega c at the transmitter end and omega c at the receiver end, both are same. Is that okay? That's why it is called coherent detection. Is that okay? Any doubts here?
The carrier frequency the cos omega city அது சொல்றீங்களா இல்ல இம்பல்ஸ் ரெஸ்பான்ஸ் வருது இல்ல சார் இதுல வந்து ரிசீவர்ல 2 omega
இல்ல
c
கேரியர் frequency என்ன frequency மட்டும் தானே, அது ஒமேகா சி மட்டும், கரெக்ட்?
ஓகே இல்ல சார் அந்த ரிசீவர்
கேரியர் சிக்னல் அண்ணா காஸ் ஒமேகா சிடி.
ஓகே
கேரியர் சிக்னல் அப்படி சொல்லியாச்சுன்னா காஸ் ஒமேகா சிடி. கேரியர் frequency அண்ணா it is omega c, correct?
ஓகே
Yes. Any doubts here? Yes, please ask doubts if you have any. Okay, so if there are no doubts, if you look at the frequencies omega c, carrier frequency, let us focus on that. It's very small or very large? Omega c is very large or very small?
Very large.
Very large. Everybody okay with that? Carrier frequency usually would be very large. So to generate a very high frequency signal, the circuitry which does that is complex. True or false?
Yes, sir.
Yes, because if you want to generate very high frequency, you can argue that sir, simple LC circuit edutha podumalla. Yes, that is fine. But what happens on the omega C maintain pannumalla? So on apart from that, we should have a control system also, which always maintains the stability of the system. Same constant frequency omega C mattum edukunomana, it is not possible. Simple LC edutha, it's not possible. So what is that you have to do? You have to stabilize the carrier frequency at omega C. To do that, what happens? Instead of just the LC circuit, we should add extra circuitry. So definitely what happens, extra circuitry you are adding, and what does it mean? It means that the circuit will become complex. Circuit becomes complex, and definitely this fellow will come into the picture. Correct? Who will come into the picture here? Money. Correct? If the circuit becomes complex, money also will come into the, that also will increase. Correct? Yes or no?
Yes.
Yes. So generating a frequency of omega C at the transmitter is okay, or at receiver is okay. Yes, think practically. Who is transmitter here? He's a rich guy or poor guy?
Rich guy.
Rich guy, right? Whoever does the transmission part, that fellow should be rich. Airtel, correct? Doordarshan, all these fellows are very rich guys. So definitely for them, generating cos omega CT and putting lot of money in complex circuitry is not a problem. Is that okay?
Yes, sir.
Yes, but receiver end, who are they? They are normal people. Aam Aadmi, can he generate cos omega CTR? Or receiver, if you say it is 40,000 rupees, and nobody will buy. Or radio 40,000 rupees, and a TV varum, nalla TV varum, they will tell like that. Correct?
Yes, sir.
So receiver should be cheaper or costly?
Cheaper.
Cheaper. Transmitter can be costly because that fellow is rich guy. Correct?
Yes, sir.
Yes.
Yes, sir.
So what is happening? Yes, fine. Mathematics is fine. Getting back M of t nalla irukku, very good. But what is happening? Practicality, if you see, generating cos omega ct is what?
Not possible.
Costly.
Practically costly. And hence what happens? Receiver becomes what? Costly. So another disadvantage of DSB-SC transmission is what?
Costly
The
receiver.
receiver is costly. What is another disadvantage? First one. Huh. Signal bandwidth is B hertz, but you have to pay for
2 plus
Double
B plus
back.
2
B
B
hertz.
hertz. So these two are the disadvantages of DSB-SC signal. What is the first one? Transmission
Higher
bandwidth is 2 B hertz. And what is the second one? Receiver is
Receiver is
costly. Okay, so please write down below that. Generating a frequency, generating the carrier frequency omega C is involves. Okay, so generating carrier frequency involves complex circuitry, involves complex circuitry, and hence the receiver becomes costly. Okay, and hence receiver becomes costly. Okay, so and hence receiver becomes costly. Okay, I will write down that note. Here I just mentioned that, but in your notebook you have written receiver is costly. Okay, receiver is costly, and hence what is that we have to do? We have to overcome these two disadvantages of DSB-SC signal. What is that? We want to make our receiver cheaper, and we want to reduce the transmission bandwidth. Okay, so that part we will see in the tomorrow's class. Is that okay?
Yes, sir.
Okay, yeah. So what we will do tomorrow here, we will make our receiver, yeah, cheaper, and also let us see how it is possible to reduce the transmission bandwidth. Okay, yes. So tomorrow first we will see how this modulation, which circuits are used for modulation. Later we will go for other two, how to rectify these two disadvantages. Okay. Okay, so it's time for us. I think I'll stop now. So tomorrow, if nothing, no information is given, we'll have at 6:30 or else we'll start at 6:15. Okay, depends upon the meetings I have tomorrow in office time. If I don't have any, we can start early. Okay, I'll let you know. Kumaran sir will let you know that. Okay.
Yes, sir.
Okay then. Thanks, sir. If you don't have any doubts, I will stop.
Thank you, sir.
Yes, boss. Bye.